And previously also I had done the same session on SVM, and I'm very glad to present this particular session to you again. SVM is a very important model in the machine learning, and I hope that everybody knows about what is machine learning. Machine learning is actually about learning some models from the data. So you will have some data as a tabular format, or as an image, or as a text, or as a video or audio. You need to learn from the data, and automatically the machine learning model learns certain things, and using that you can do tasks like a classification, and then you can do something like regression. Classification means you want to label a sample. You can give a label to the sample, whether it is a image of lung cancer or it is not a lung cancer. And you can do regression. Regression means prediction of real numbers, where you can do something like based on the data you can predict what will be the weather for tomorrow, what will be the temperature for tomorrow. Okay, so there are many things are possible with the machine learning. And there was a time this support vector was actually the heart of machine learning, where many of the classification problems were solved by the support vector machine with a high level of accuracy. And support vector machines are really powerful because of their like theoretical background and like a practical performance. Okay, so we'll see all these things today. And before going to the support vector machine, let me give some kind of small model before support vector machine, then we'll move on to the SVM. Okay, so in the data set you have something called features. Okay, and from the features we want to learn things. If you have a data set which is actually a tabular data, then your columns are your features and your rows are your samples. You know, for example, you have maybe the list of girls that you dated. Maybe if you are keeping a list of that, the columns are the features of the girls and the rows are the samples, like girl 1, girl 2, something like that. Okay, and the features of the girl will be like serial number, name, and then age, then maybe her education, something like that, if you are maintaining such a list. Okay, and based on the features we need to detect a target from the data set itself. Okay, for example, some problems we try to predict the house price, where the features will be like a number of rooms, house area, air pollution, distance from facilities, economic index, security ranking. All these are actually the features, and these features are the independent features which doesn't depend upon anything. And this house price is a dependent feature, where the price of the house depends upon all these features. Okay, and we want to predict the price of the house using these features. You want to learn the machine learning model using these features, and these are the columns of your data set. And for speech recognition you have like speech related features like a filter match, and then power, length, and then noise ratio. For images you have pixels and curvature, age. All these are your features. For emails and server attack you have like IP address, timing, location. Whatever that is related to the problem becomes a feature, and based on the feature we want to actually predict the target. Okay, let us take the problem of maybe house price prediction, and let us do a small analysis how we can actually do the prediction. So meantime, if you have any doubt, please let me know. Please don't hesitate to ask any question. Okay, please don't live with the doubts. You know, whenever you have doubt you have to get rid of it as soon as possible. Let's say that you want to predict the price of the house, HP, and you are going to do it by considering the BHK, the area, the population, and the pollution. Now feel free to like unmute yourself, because I want to interact certain things with you. I want this session to be very interactive. So you have like a lot of features, whether all the features are important or only some features are important and some features are not important. Anyone? If you want to predict the price of the house, do you need to consider all the features or only some features are important? There is a chat box also, you can post your messages there. Some more features, some more than features. Matlab? Okay, some features are important. I think that is what you mean by say. Some features are important, some features are not important. For example, if you are having a column like serial number, I don't think like serial number has anything to deal with the house price. Similarly, the name of the house. You can name your house like Rashtrapati Bhavan, but the price is not going to change just because of the name. You know, we can name our house like Taj Mahal, White House, Qutb Minar, but that has nothing to deal with the price of the house. Nobody is going to pay a high money because it is named Rashtrapati Bhavan. You know, Rashtrapati inside the Bhavan. You know, so some features are important, some features are not important. Okay, we can say, okay, let's say that these are all the important features. All the important features are equally important, or they are like maybe relatively important. Some are more important, some are less important, or we can say that all of them are equally important. Can we treat them everybody equally? BHK, area, population, pollution. Anyone?
No, sir.
Yeah. Some features are important. Some features are like relatively more important. For example, BHK that plays like really a vital role. You know, 2 BHK 2 lakh, 3 BHK 3 lakh, something like that. And then the area, even if you increase the area by maybe 1000 square feet, you're not going to see a big change. Okay, and all these features actually have some kind of correlation with the input. You know, when you increase the BHK, the price of the house also increases. So we can say that this BHK has a positive correlation, because sometimes you decrease the BHK, the price of the house should be decreased. Okay, and what about the area? If the area is more, the price should be higher. So again, there is a positive correlation. If the area is less, price should be lower. Population. If the city is highly populated, then again the price will actually go high. And if the city is less populated, then the house price will actually go down because of the land value. And this is actually the positively correlated feature again. What about pollution? I live in Greater Noida near Delhi, and here there is a lot of pollution, and we are ekdam number one in India. You know, so if the pollution is high, then the price of the house should be lower. Okay. Sometimes there are dump yards nearby the home, and you have to pay a lesser price for the dump yard. So this particular feature has a negative correlation. You know, and there are many features which are positively correlated. There are many features which are negatively correlated. And there are some features which are zero correlated, like serial number. That has no correlation. Either you increase the serial number or decrease the serial number, it has nothing to deal with the price of the house. Now my question is, can you name any other negatively correlated feature for the house price? Where you increase the feature, the price of the house should come down. Anyone? Ajao, bhai or behan, come on, everybody wake up. This is only afternoon. You might have had a heavy meal, but don't sleep today, okay? Today is Friday. You might not have any non-vegetarian. Everybody wake up. So can you tell any other negatively correlated feature where you increase the feature, the price of the house should be coming down?
Location.
Location. So how we can say like location is a negatively correlated feature?
If location is very far from the
Yeah. Like how far is it from the we can say like a distance from the city? If the
Distance.
distance is more, yeah. If the distance is more, then the price of the house should be lesser. You know, sometimes people try to bully you and then sell you a wasteland which is very far away from the city. They'll just say like, yeah, it is very nearby the city, just 70 kilometers away from Pune. It's in the city itself. What the hell? Every 70 kilometers is like outside Pune. You will reach some other main city there. And they will say like, yeah, there is a hospital nearby. In 50 kilometers, you will just reach it within 2 hours if there is an emergency. We are going to die on the way, you know. Sometimes it happens. Any other features? Distance is a nice feature, negatively correlated feature.
Sir, pollution.
Pollution, yeah. Pollution is again a negatively correlated feature. When there is a more pollution, price out should be lesser. Any other? There are many actually. When you want to buy a home, there are less positive features and there are more negative features. Okay, there are some messages in the chat. Crimes in the neighborhood, yes. Municipality features, yeah. Municipality feature has a positive correlation. Crime, you know, if there are a lot of gundas and rowdies, gangster people near the home, then in the night time they just start drinking and dancing for no reason. You know, you don't want to live there. Okay. Similarly, ghost. Sometimes you have like booths in the bungalow. It's a booth bungalow. You don't want to live there. There are like a lot of Lakshmis, Kanchanas, Gangas. You don't want to live there. You don't want to live in a place where there are a lot of ghosts. If there are more ghosts, then the price has to be lesser. Okay. So this is the dependent variable that we want to predict, and this is the independent variable x1, x2. Anyway, you get the idea, right? x4. And can I just like add them directly? No, right? Because you cannot consider them equally, and they have a relatively different influence. So what I'm going to do, I'm going to like give a notation for all these correlation values, and I'm going to say that it's going to be a weightage for each and every feature. Okay, if there are 4 features, then you'll have 4 weightage: W1, W2, W3, W4, up to like Wn, Xn. So the weight, this is actually something called weight. The weight will tell what is the correlation of this x1 corresponding to the y. And here the weightage will be positive because the BHK has a positive correlation. And this population is also like positive. And after the training, this pollution, this weightage will also become negative. And again, this model can be represented simply using like I is equal to 1 to n wi xi. This is a very simple thing. Or we can just say that maybe W transpose X. Imagine that this is a column vector and this is a column vector. If you want a dot product between 2 column vectors, you can just transpose one of them and then multiply. And this is a dot product between your weight vector and your input vector. So we can say that y cap is equal to W transpose X. And the problem is, who will find this y value, W value? Who will find this proper W value which can actually build a large number? This is literally like you want to build a number based on taking different proportions from your input. Okay. And what we are going to do, we are going to use an algorithm called gradient descent to tune this particular weightage and get a proper weightage for the entire data set. Okay. And that will be done automatically. And now this is our model. This is a model called a linear model. It's a linear model because you have a linear multiplication of weights with the input. Okay. And whenever you are going to learn the weights automatically, you are going to initialize the weights using small random values. Okay. Small random means the weight can be like minus 0.005 or plus 0.00075, something like that. Small random value. And when you are using the algorithm gradient descent, it will automatically like change and then you will reach to the proper values. Okay. Okay. All right. So let's see a very simple model. Weights are the ones which you want to learn, and learning that weight is actually called machine learning. Okay. You are learning the weights. All right. Let's see a very basic model, linear regression model. It's a very, very simple model in the literature. Imagine that you have only 2 columns in your data set, x1 and y. So the x1 is actually plotted here and y is actually plotted here. Based on the x1, we want to predict the y value using a linear model. So all these dots are your samples. Samples are nothing but your rows of your data set. And let's say that there are m is equal to 200 examples. There are 200 samples. This is a scatter plot. And you can generally see that when the x is increasing, the y is also increasing in most of the times. So they have like a kind of positive correlation. So very simple way to fit this particular data is by fitting a line. Very simple. Y equal to mx plus c. This is the equation for the line. And m is your slope. The slope will tell whether there is a positive correlation between the x1 and the y or there is a negative correlation. So here the slope will be positive because the change in the x is actually causing positive change in the y. That is the role of your slope. And the value of c is actually the intercept. That will tell you what is the value of your output when x is equal to 0. So it has the intercept which is here. So the entire model can be represented using 2 parameters like y is equal to mx plus c. Now instead of m, we are going to give a notation y cap is equal to w1 x1, where this w1 is actually the weightage you are giving to the input, plus instead of c we are going to call it b, bias. This is going to be called as a bias. Now this is the extra parameter which is actually telling you what will be the output when the input is actually 0. And we call it a bias because it is independent to the input. You have nothing to deal with the input. Even if your input is 0, the output of the model depends upon the bias. Now this model is actually called as linear regression model. I have a question now. Is it possible to fit this data with a simple model like y cap is equal to w1 x1? Oh, I'm able now. Like I got, yeah, sorry. There was a power cut. Is it okay now?
Yes, sir. Yes, sir.
Okay, madam. Sorry. All right. Yeah. So my question was, for this data set, for this kind of data, can I fit a very good model with the y cap is equal to w1 x1 without the bias? Will the model be good?
I think yes, sir. I think yes, because all the points are linearly correlated.
Okay.
Yes.
Okay. So if I actually fit a model without the bias, then the model will actually go through the origin. Do you think that the model which is going through the origin can fit this data well?
No.
No, sir.
No, sir.
No, sir.
Yeah. So the thing is, sometimes your data can be something like this, right? It can be above your origin. It doesn't like always happen that always your data goes through the origin. It never happens. Sometimes your data is actually above your origin, sometimes it is below the origin. And it is not possible to fit a model well using a model which is just going through the origin. So the rotation of the model can be based on the bias, sorry, weights. This is the rotation of the model. Whether you want to fit the model like this or whether you want to fit the model like that, okay, that depends upon your W. But where do you want to fit the model? Whether you want to fit the model here or through the origin or below the origin, that depends upon your bias. Okay. So there are two properties of your model. One is the rotation part, which is the correlation with your input. And other one is where do you want to fit the model? Whether you want to fit the model here or here or here, here. So that depends upon the bias value. So for any good model, we need two parameters, which is weights and bias. But again, I'm not saying that the bias is actually mandatory. We can fit a model even without the bias also. But bias is actually a very interesting parameter, which will give you a relaxed fitting. Okay. If your data is zero centralized, for example, if your data goes through the origin and your model also can go through the origin, in that case, you don't need a bias. Okay. All right. So how do you evaluate whether the model is actually doing a good work or not? You need to actually find whether it is doing a proper prediction or not. So to do that, you need to find what is the difference between the actual value and the predicted value which is on the line. For example, for this model, if somebody gives an input of 50 and the model will predict as somewhere here, like 12. And then you need to know what will be the error for this prediction 12. So we need to calculate that error for all the samples in your training set. That can be done using this simple method, mean squared error, where you compute the difference between the predicted value and the actual value and you take a square. And you take a square, both negative and positive errors will become like a positive only. And you take a sum and then take an average. That is a mean squared error. And for a good model, this mean squared error should be minimum. Okay. And we mentioned that the bias and the weights will be initially near zero, like small random values. and your model will be sleeping somewhere here. Okay, and using the gradient descent algorithm, there is a algorithm called gradient descent. I'm not going into details of this algorithm, but this algorithm will help you to like iteratively improve the weights and bias to a proper one. Okay, so what will happen? For the initial weights and bias, it will compute the mean squared error, then it will adjust the weights and bias. So now your weights and bias will be like increased and your model will become like this. Again, it will compute the error and then it will try to adjust the recent weights and bias. So iteratively your model will start getting up and then moving towards the proper value. At some point, your model will actually come to a like good position. And there, the error will be minimum for the entire data set. Now I have a question. Is it possible to have a mean square error which is equal to 0? Is it possible with this data and a linear model?
No, sir.
Why, madam?
No, sir.
Because all points.
Yeah, all the points are actually scattered. We cannot actually expect that the data will be like somewhere looking like a line and we can easily fit a line. It never happens like that. So there is always like a plus or minus value for our prediction. That is totally okay. And we don't want to actually go through each and every sample of your data set, because that is like memorizing your training set. And your like future data samples might not look like the training samples. So it is totally okay that we have some kind of mean squared error. We want a minimum error. We cannot have a 0 error. Okay. So that is something like everybody want their sons or daughters to be a good fellow. You know, everybody will like their sons and daughter if they behave well, and if they behave really well, they are very happy. But no mom or dad likes a son and daughter to become a monk or a Swamiji or a Guruji who is giving up the entire life and not doing anything. Too much of good is actually also it's very bad for the society, also for the family also. You need to have some kind of craziness. Okay, you need to have some kind of error in the model also. So we don't want a 0 model error. Okay, we want some error so that we believe that the model will generalize for the future samples. Okay, now this linear regression model can be extended to multiple inputs also. Let's say that we want to predict the price of a computer. Screen size, hard disk size, process speed, RAM speed, battery time, all will become your input, and these are all the weightage that you are giving for each input, and along with them you have a bias parameter also, which is getting an input of 1. So that is like 1 into bias. So we can say that the input to the bias is 1. Now what we are doing here, we are computing W1x1 plus W2x2 plus W3x3 up to W5x5 plus bias. So again, this can be written something like W transpose X plus B. So if your problem had 5 features, then your model will have 5 weights plus 1 bias. So there'll be 6 parameters which you have to train it. So sometime what happens is, if you want to give a output in a proper range, what you will be doing, you will be like converting this Z value into a desired output. And to convert the Z into a desired output, we'll be using an activation function. This is a kind of like transformation function. Before you give a final prediction, you try to transform your Z into a proper value. Okay. And in the linear regression, you don't do any activation, you just give as it is. The Y cap is actually the Z. You don't do any transformation over the Z, you just give it as it is. Okay. So this is a linear model and this is your linear regression. And sometimes people call it like multiple linear regression, but it doesn't matter. A linear regression means it can take like multiple inputs also. You don't need to call it like multiple linear regression. Okay. So very, very simple. Again, this linear regression model can be trained using the gradient descent algorithm by minimizing the mean squared error between our prediction and the actual values. Right. For a good model, it will actually give a very small error. Now I am going to throw a question. If I have a particular maybe an input called the age, that is like x6, and you have a corresponding weight called w6. After training the model, what will be the sign of this particular w6? Whether it will be positive or negative. I am including the age of the computer here as a x6. And what will be the weightage after the training?
I think, sir, plus only.
No, madam. I think negative. Yeah.
Okay.
Yeah, Vignesh Patrikar. Yeah, he has given a right answer. Some people in the audio chat also they are giving. So that is actually the correlation that you are actually like giving to the S6. So if the computer is like old, then the price has to be lesser. You cannot say like old is gold. Lelo buy. My computer is 15 years old. It's 50,000 rupees. Lelo. Nobody will buy it. Okay. So that old is gold can be applicable for bungalows and artifacts. That cannot be for electronic items. It's my Pentium 6. Buy it. Pentium what? you know okay, now I want to convert this problem into a classification problem. For example, given a configuration, you need to decide whether it is a good configuration or a bad configuration. How do you do that? You want a binary output. Your inputs are all like maybe real numbers, and your weights are actually real numbers, like floating point number, positive as well as negative. And if you are multiplying a real number input and a real number weight and then taking a whole summation, your Z will surely become a real number. I mean, floating point number. And how do you convert a floating point number into a binary value? Like what you can do so that your problem becomes a classification problem. Anyone? So the like clue is here in the activation. What we can do? Okay, so set a threshold value. Yes, Mr. Akshay, you are right. Below it is 0, above it is 1. Yes. Yeah, just like how people used to grade other people, whether you pass the subject or not, whether you pass the exam or not. You just set a threshold value. You say like more than 35 is pass, less than 35 is failed. And the people who got failed, they'll be fed up. What the hell, man? Lower the threshold, goddamn it. Set the threshold as 15 so that we'll also pass. Then after some time they'll say like, yeah, screw the system, man. I don't like the marks. A mark cannot decide my fate. And then he'll become a YouTuber and then cross million subscribers after a year. Then he becomes like a millionaire. After a year, the school or college people, they'll bring him as a chief guest. That will happen. So we have to like set a threshold. Setting a threshold is a very simple thing. So here in this problem, we can actually set a threshold of 0. If your Z is greater than 0, then your Y cap will become 1. If your Z is less than or equal to 0, then your Y cap will become 0. Okay, so let me just clear this entire slide and give it to you. Yeah, so we are going to use the activation function, which is the threshold. If the Z is greater than 0, Y cap is equal to be 1. Z is less than or equal to 0, the Y cap is actually 0. And this particular step function, activation function is actually called a step function. Okay, if the Z is more than 0, then your value will be 1. If it is less than 0, negative value, the value will be 0. Okay, and this is your Y cap. So this particular function, thresholding function, is called a step function because it looks like a step in your staircase, one of the steps. Now there is a issue with this step function. Can anybody tell that what may be the drawback of this particular step function? What do you think? Yeah, categorized by threshold. Anybody? What do you think? If there is a staircase, then you have like more possibility you will fall down sometime. Here the same problem is there. Can anybody figure out like what is the problem? Do you think like binary is actually good for life? Binary is not actually preferred in the machine learning. Having a binary output, sometimes it is not preferred. So I'll tell you a technical problem, what will actually happen. If your Z becomes a like small positive number, 0.0005, then your model will say like y cap is equal to 1. Then if your result is like minus 0.000005, then your model will be like y cap is equal to 0. Then you'll be telling the model, you stupid goddammit, both of these numbers are actually near to 0 and they don't have much difference. They are just small numbers. The difference between them is very, very narrow. How the hell you can say that this is actually y cap equal to 1 and this is actually y cap is equal to 0? The model will be like, yeah man, I just put a threshold 0. Whatever more than 0, that is called y1. Sorry, that is called 1. Whatever less than 0, that is called 0. So the transformation between your class 0 and the class 1 is actually very narrow, and it just happens because of the signature, you know. So the model will actually not like sometime learn anything, because your weights will be still positive number, small positive number, small negative number, and it just needs to find a difference in the signature only, just to give a output. Okay, and most of the times the people don't like a binary output. They want like a probabilistic output. You don't want the model to say like it's a good computer. You want the model to say like, yeah, it is a 95% good computer. Or maybe if it is a 55% of good computer, you want to decide whether to buy the computer or not. Sometimes it will say like, yeah, it is just 15% good computer. The configuration is only 15% good. Okay. So what you want is actually a probability in the range of 0 to 1. That is what we want. Okay. So now this model, a linear model with the step function as an activation function, is actually called a perceptron in the machine learning. Perceptron is actually one of the earliest neural networks, which was discovered in the 1950s or 60s, and very powerful model back then, implemented using physical wires. Okay, and this is a linear model, and which will always give a binary classification output, 1 or 0. Okay, now we have a solution. We want to convert this like a hard thresholding function, a step function, into a softer one. You want to smooth it out in the range of 0 to 1. Can anybody tell any way to achieve this? How do you smooth this function?
Sigmoid function is there.
Yeah, yes, madam, yes. So this kind of behavior can be obtained using a sigmoid function. Okay. So anybody, even if the data is close to pass through, it still output will be 0. Yeah, yeah, yes. Yeah, that's the thing. Yeah, in the literature of mathematics, there is a function called a Stigmoid function, which will take any input in the range of minus infinity to plus infinity. So the function is actually like this: 1 by 1 plus e power minus z, where z is actually the w transpose x plus b. Okay, which is actually this value, and you can just compute the 1 by 1 plus e power minus z to compute the output in the range of 0 to 1. Okay, and the sigmoid function will have a structure like this. If your input is 0, if your z is equal to 0, then your output will be 0.5. It says like 50-50, and if your z becomes positive, then your output will be more than 0.5. So means like you can later set a threshold like for a good computer the output should be more than 0.5, but that we can do later. But we want the model to give some number like 0.75 or 99, something like that. Okay, if your number input z is equal to 5, then your output will be like close to 1, and if your number is like negative 5, then your output will be close to 0. Okay, and this sigmoid function is sometimes called a logistic function. And if you are using the logistic function or the sigmoid function as an activation function with the linear model, that model is actually called as logistic regression. Okay, again, logistic regression is a binary classification method, but it will give a probabilistic output 0 to 1. Okay, the word regression means like a prediction of a real number, but logistic regression is actually a classification model. It just tries to predict in the range of 0 to 1. Okay, otherwise logistic regression is a classification model only. It is not a regression model. Okay, regression means prediction of real number. Classification means you give a discrete label, something like cat, dog, stupid versus not stupid, something like that. Okay, all right. So let us see one example for the logistic regression. Then we will move on to the further part, SVM and all. Okay. Let's say that somebody want to build a logistic regression model for a marriage proposal. Let's take an example. I have a friend called Rishi. He's living in Delhi. So let's say that Rishi has visited maybe hundreds of houses for marriage proposal. I mean, not randomly. After going through a lot of profiles in the matrimony, he shortlists somebody and then he likes the girl and then he visit the home and then for some reason all the 100 people said no to him. So now Rishi is fed up. What the hell, man? I don't want to go to somebody else's home and then says that I like your daughter and they say no, we don't want you. I just want to develop a machine learning model which can actually do a kind of classification before the visit. So sometimes Rishi likes some girls and then sometimes Rishi did not like some girls. So what he wants to do, he wants to build a model which can predict whether he will like the girl or not. Okay, based on the existing data, hundreds of CVs and hundreds of his preferences, whether he liked them or not. And let the model give some kind of probability, and based on that, he will decide whether to visit the girl's home or not. Okay, sometimes he doesn't like her, sometimes he likes her. He doesn't want to visit the places where sorry, I'm getting a call. So sometimes he doesn't want to go to the house if the model says the value of 0.1 or 0.2, something like that. So he wants to visit only if the model says that he's going to like her. Okay. So these are the different features that he's considering for the marriage proposal. Family background, salary, smoking habit, cooking skill, morals. Okay. And please don't get it otherwise. This is actually gender biased skills. Sorry, gender biased features. Most of the time in the Indian systems, we are bound to this, whether the girl can cook and then whether she has some morals and that family background should be there. Okay. But these days, things are changing that these features can be applied to men too. The girl will expect no, I don't want to cook. Let him cook. I will go to the office. So we have different preferences and priorities. And these priorities are represented using the weights. And how much you are giving to the family background as a weightage. So sometime your family background, the girl's family background can be positive. It means a good family. -1 means maybe a rowdy family, gundas and thugs are there in the family. Maybe -1 also means the girl has 5 brothers. I don't want to marry a girl who has 5 brothers. Don't do that. For some reason, if the girl cries, one of the 5 brothers or 2 of them will gang up and then beat you for no reason. And they'll beat you and then they'll ask you what the hell? Why my sister is crying? Then you'll be she was watching some TV, man. She was watching Nagini. What the hell I have done? Okay, don't make her cry. Then they'll leave. Okay. Similarly, salary. +1 means she's earning salary. She's a kind of a giving salary type. -1 means she's taking salary. She'll be give me your salary. Half of it. I'll run the home and then I'll save rest of the money. Then smoking habit 1. +1 means a few packets a day. Okay, not a heavy smoker, only 2 packets. -1 means she doesn't know how to smoke or she hates smoking. Cooking skills. +1 means she wants to cook. -1 means Swiggy or Zomato type. Whatever you want to have, you can just order. +1 means she has a kind of orthodox mentality, good morals, good ethics. -1 means my life, my rules. Nobody can control me. I'm a butterfly, something like that. And these weights will represent what he likes about a girl. If he wants a positive family background, his weightage will be positive. If he wants a negative family background, if he liked all the gangster families, then his weightage will be automatically negative. Because the negative input multiplied by your negative weight will become positive. That is what we call wavelength. You have person 1 and then person 2. Somebody will say yeah, I like Salman Khan, and they'll be yeah, man, I also like Salman Khan. Man, I hate Alia Bhatt. Yeah, man, I hate Alia Bhatt. Yeah. Then I love Jetix. I also love Jetix, man. This is actually called a wavelength. People with the similar interests. So this goddamn it, Rishi is actually looking for girls with the similar interests. Whatever the weights are, if the input is looking similar to that, then he will get activated. Okay, so salary, if he wants a girl with a salary, then it will be positive, and for a like a girl who is smoking, he will give a negative weightage, and for cooking he will give positive. Sometimes people are foodie, they'll give a positive weightage for cooking skill, and then moral they'll give a positive, and bias will be there. And here the W will be multiplied with all your x's, and you compute the z value. Z is equal to W transpose x plus b will be there. Since it is a logistic regression model, the activation will be the sigmoid function 1 by 1 plus e power minus z, and then your output will actually tell you whether to go for the marriage proposal or not. And if the model says that the 0.99, then Rishi has to visit that home. Otherwise, he is going to avoid the visit. You know, otherwise, why to sit in somebody's house and then tell them like they don't like them in the face, and then they smile after that. Rishi don't want to embarrass himself or the family of the girl. Okay, so he wants a machine learning model. Now we are going to do a small analysis. Let's say that the model actually says 0.99. What does it mean? What does it mean if the model says 0.99? It means the activation of the model is actually going to the like this direction. I mean, you got a high activation, right? Which is like close to 1. So that means your input z should be a positive number. Only then your output will actually become more than 0.99, because according to your sigmoid function, the output will be 0.99 only if your z value is actually a positive big number, 1 by 1 plus e power minus z. And this z should be more than 5. Only then this output will become 0.99. Okay. And the thing is, if you want this z to be more than 5, then this W transpose x plus b should be giving more than 5. And that means both the weights and the inputs should be looking similar. You know, only then you will get a z value which is more than 5 and your output value which is close to 1. Okay. Let's see a numerical example. Somebody comes with the input like positive family background, positive salary, smoking habit is like 0, and his priority for the smoking is also 0. Okay. And cooking skill and then morals. So for all these, he has a weightage like this 1 1 0 1 1, and the bias is 1. So if you do a computation like this, then your z will become 5. If your z is 5, then your output will become 0.99. That means both of them are actually matching. Like whatever he is expecting is actually satisfied by the input x. Okay. Imagine that Rishi is expecting a positive family, positive salary, and a smoking like should be 0, and then cooking could be like positive, and then moral should be positive. But the girl comes with the input something like my family is a third family, a negative salary, I don't want to cook, I'm a free bird. What do you think? Now all your inputs are negative and your weights are positive. Then if you do a W transpose x plus b, here the output will be -3, because you have like -4 plus this bias 1. It will be -3. If your z becomes -3, then your output will actually become close to 0. That will be something like 0.01. So that means she is not a match. What you are expecting is actually not fulfilled. Okay. So you have 4 scenarios. You have 4 scenarios in your model. You have x, you have weights, you have z, you have sigmoid. If your input is positive and your weight is also positive, positive into positive will become positive, and your sigmoid will become near to 1. If your input is negative, your weight is also negative. Negative into negative will become positive, and your sigmoid will become 1. If your input is positive but your weight is negative, or your input is negative and the weight is positive, in both of these cases, your sigmoid will be close to 0 because of your negative z value. So it is not like all the values will be positive, all the values will be negative. Sometimes it may happen like this also. You are expecting a negative and she is also giving like a negative value. You hate something, she also hates something. Okay. So we can say that the activation is a kind of like finding a similarity between the x and w. Okay. It will be activated only if these two matrices are looking similar. whatever you are looking for, if it is coming from the input, you will get activated, you know. Sometime you go to college, man, I miss those days, man. These days we open our system, that is our college literally. Those days, you know, last year. Sometime we go to college, and then in the morning itself, you actually like get a lot of response from your friends, like, hey man, how are you? And then people say that you are looking good and then handsome. Then you feel really activated because you are expecting some kind of positivity from the people, and they are also giving the same kind of thing. Okay, you feel highly activated, you feel energized. Sometimes it doesn't happen like that. You know, Monday morning you go and then people don't really care about you. You know, the girl you like, she's like talking with her bestie. You know, and you got fed up. What the hell, man? Then one of your close friends says that, why, where you bought the shirt? It's shitty, man. You should not, you should not bought it. And then you feel like, man, I have spent like 1,500, and then you are saying that this shirt looks like city. So you feel like deactivated. This Monday morning itself, your lecturer like scolds you for no reason. Where is the assignment? And then you are like, was there assignment? Nobody told me. You are expecting something, but the environment is giving a totally different input. Then you feel deactivated. Then you feel like, my energy is low, man. I'm gonna go home. You feel like you want to go home at 11 o'clock in the morning itself. You know, that is the kind of thing. The models are exactly like humans, you know. They are also expecting something, and if the input is like similar, then you feel highly activated, and the model will give a high activation. That's the reason why people actually call it as an activation function. They'll give a high value only if there is a similarity. Otherwise, this activation function will just like suppress it to a zero value or a negative value. Okay, so there are a lot of activation functions which can give the output in the range of 0 to 1 or 0 to infinity real number, -1 to 1, or sometimes linear will give like a minus infinity to plus infinity. Okay, so there are a lot of possibilities. So linear regression model is actually just without any activation, and the logistic regression model is a linear modeling with the sigmoid activation, and the perceptron is actually a linear modeling with the step function as an activation function. Okay, so we have seen three models in the machine learning: one for regression, linear regression, and two for classification, perceptron and logistic regression. Any doubts?
Sir, for this bias value, always we take 1.
No, madam, that is actually depending upon the model's overall expectation.
Okay, so that is a part of survey to find out the optimal.
Yeah. The gradient descent model will automatically find what should be the proper bias value. And again, just for numerical example only, I have taken only the binary values. But in real life, when you train the models, all these values will actually become like what do you call real numbers. And the input also will be like in different range. Usually, you know, like for problems like let's say that you want to work with the computer price prediction.
Yes.
Screen size will be in inches and hard disk size will be in GBs. Process speed will be in gigahertz. RAM size will be in GBs. Battery time will be in hours. So all of them are in a different range. And if the values are in different range, then the model will like sometime get confused to give a proper value of W. So what we will do, we will try to normalize all these input values into the range of 0 to 1 or -1 to 1, so that we can let the model to decide what features are more important, you know. And sometimes when you train the model using gradient descent, even after the training, if you find that maybe one of your weights are still near 0, it means the model just found that the input has nothing to deal with the output. It is a unimportant feature. That is what the model's parameter will tell. And that you can find it after training the model with the gradient descent. So you can find the feature importance also, like whether the feature is actually important. If it is a large positive number or a large negative number, that means the input has a lot of contribution to the output. Okay, we can use it for feature selection too. All right, so we have seen three models. Now we are going to move to the requirements for a SVM, like why the hell we actually need a SVM. Okay, before that, if you have any doubt, please let me know. Any doubts, please feel free. Please don't think like the doubt should be like a high level of question. It should not be like a very simple question. There is nothing like a simple question or a complex question. Question is a question. Okay, if there are no doubts, then I will assume that maybe you're all clear with the concept. Sometime if you don't know like what the hell I'm talking about, then also there won't be a doubt. But I'll just assume that everybody understood everything. Okay, all right. So this logistic regression, what it will actually do is like it tries to draw a line between two classes. Not just logistic regression, any linear model like perceptron or logistic regression. It is trying to draw a boundary. So this is actually represented using your W1 and W2. Okay. So this is actually called decision boundary. And if the model is actually able to draw this boundary where both of your classes are actually separated, then this model will have a like really good training accuracy of 100%. Okay. And this is actually called a discrimination. Discrimination means you want to actually draw a line between two of the classes. This is like a gang A, and then this is like a gang B, and both of them are actually opposite to each other. And you want to separate them. You want to separate them, that where is the line? So that when somebody comes new and then says that I belong to this position, your model will say like, oh, he is falling under this line, should be a gang member of A. And if somebody says that I'm here, yo, then your model will say like, yeah, man, this guy belongs to gang B. Okay. But there is a problem with this kind of model. You don't know that, but there is a problem with this kind of model. If the data is actually well separable, then there is an issue. Actually, there are many lines possible. If your data is actually having this kind of distribution, you can draw any line. And all these models, all these lines will have a training accuracy of 100%. But only one of the model will actually do a good job in generalization. What the hell we mean generalization? Generalization means for the unknown sample, we have to actually give a prediction. That should be a proper prediction. So we can see that this model is like having a totally negative like slope here, and this is doing a poor job because this sample is like very close to this sample is very close to this. What about this one? This particular line is close to this blue class and it is very far away from the red class. So if somebody comes here, then the model will probably think it becomes a red class, but it is like maybe it is belonging to the blue class because it is close to this area. Okay. So that's a problem with the different models. So this is bad and this is bad. What about this one? This is also bad. Again, this model is actually close to these samples and they have like a lot of distance with the other class. And this one is also bad because sometime maybe like a sample comes here, but it may belong to this particular class. Okay. This one, also this one, also this one. So all these models, they will have 100% of training accuracy, but the testing accuracy will be totally like very bad. That is because none of these models actually try to draw a line which can balance between both the classes. They just draw a line to separate them. Okay. So in my opinion, a good model will look like something like this. Okay. Which will be in the middle of both the classes. Okay. So now we introduce a concept called margin. We want to find what is actually the distance between the samples and the model. And for a good model, this margin should be maximum. That is like there are two gangs of people and you want to draw a line where the line is actually having similar or maximum distance between the gang members. You don't want to draw a line which is close to one of the classes. You just want to like draw a line in the middle. Okay. So that this line can generalize for the unknown samples. Any doubts? Okay, so now we are going to still deal with the model W transpose X plus B. Okay. And we want to do some changes. Okay. So maximum margin is actually a model which can just like go in the middle of both the classes and have a maximum margin in between the class A and the class B. Okay. So this is the model and this is the margin, and the margin is actually maximum. For all these other models, the margin is actually minimum. It is like very, very close. Very, very close. So we want to build a model which has a maximum margin. Okay. We should understand one more thing, that whenever you are like training a model, the model is actually maybe training something like this with the random weights and biases. So let's say that initially your decision boundary is falling here, and after some time it has to like come to this place. Okay. It will come like this, it will come like this, it will come like this. Then immediately when your model is actually giving a zero error, and your model is saying that I have actually successfully separated my model, both the classes, then we cannot expect the model to further train and then actually give a maximum margin. This will not go from here. Whenever you are training and once you reach the proper accuracy after some time, just when you reach here, the model will stop the training because it has reached the 100% of accuracy, and your loss is also like a very minimum, maybe a zero value. And from here we cannot expect the model to actually reach to here. Okay. We need to now enforce the model to actually go to the middle of the entire distribution. How we are going to enforce it? Okay, that is the question. So this is the optimal hyperplane which is having a maximum margin between both the classes, and these are the boundaries, like, or the lines which are separating the two classes. Okay. So maximizing this particular margin is actually called a maximum margin classification. Okay. In the SVM we try to achieve it. We try to achieve the maximum margin classification, okay, through two things. We'll see one by one. So the optimal hyperplane will be like W dot X plus B. That is just W transpose X plus B. Okay, that is a model. And that is a hyperplane. You know, hyperplane means like there are like maybe one samples which are here and other samples which are here. So you have a plane which is actually separating them. That is a line. If it is like maybe a 3D data, then your line will actually become like a 2D plane, like a sheet of paper. If it is a multi-dimensional data where you have multiple features, then your model will actually become a hyperplane, you know, hyperdimensional plane, hyperplane. And this is the margin, the one which is actually with the dotted line. This is the optimal hyperplane. And the samples which are falling on top of the line is actually called support vector. Okay. And this is very important, because we are going to use this support vector for some purpose. You know, the support vector machine has the word support vector itself. We are going to use it for a purpose. Okay. Now any doubts? This is the simple model, maximum margin classification. So support vector machine has like two concepts. One is the maximum margin, finding what is the maximum margin, and the other one is the support vector. Support vectors are the samples which are falling on top of the margin. Okay. So here all the four samples are actually the support vector. For class red we have 3 samples, for class blue we have 1 sample. Okay. So there are two things in the SVM model. One is the maximum margin, other one is the support vector. So we'll come to the support vector part later, but let's see like what is the maximum margin. Okay, how do we maximize the margin? If you have any doubt in the middle, please let me know. Okay. So these are the some common terminologies which are used in the SVM. A hyperplane, which is actually separating the two classes with the maximum margin, and we have support vectors, then we have boundary line. Boundary line is actually the margin, which is dotted line. Okay. So what the SVM model will do, SVM model is also based on the W transpose X plus B. Okay. So sometime instead of W, people will prefer to use the value theta. Okay. And sometimes instead of weights, people will just call it like parameter or coefficient. Okay. Or the model parameters. Sometime instead of theta, people will use beta. They will say like beta transpose X. The notation may change, but the like influence will never change. Okay. So here we have a support vector model, which is actually G is actually the activation function, theta transpose X. Okay. And your G of Z is actually just Z. So here in the SVM model, we don't use any activation. Okay. But we are going to enforce our model to actually reach to the maximum margin. This is our theta vector and this is our input vector. This is the input to the bias. Okay. So how we are going to enforce the model? How we are going to do that? Before that, let me introduce a loss function which is used in the classification problems. In the regression problems, you are like come across this mean squared error, right? That is a squared error between your prediction and the actual value. But in the classification, since the problem is actually about probabilistic prediction, you cannot use the mean squared error as a like evaluation function or activation function. Sorry, loss function. Okay, you need to use a function called cross entropy. To find whether the model has made a mistake, you need to use this one. Okay. So that is minus y log y cap plus 1 minus y into log 1 minus y cap. This particular function is called cross entropy function. Okay. For example, if your y is equal to maybe 1, okay, and your prediction y cap is also near 1, 0.99, okay, and if you apply this particular value to this function, this second terminology will be like 0 because 1 minus 1 will actually become 0. So only the balance first will be there. So that will be minus of 1 into log 0.99. Now if you just plot the log of x minus log of x, it will look like this. Near the value of 1, this will be a small number. Near the value of 0, it will be a large number. So minus log of 0.99 will actually become a small number. And that means the prediction value should be near 1 and the actual value is also near 1. Imagine that instead of 0.99, the model has given something like 0.01. What we should have predicted is 1, but what the model has predicted is 0.01. Then in that case, minus log of 0.01 will become a large number. It means we made a huge mistake by giving a mistake in the model prediction. Okay. Similarly, if your y is equal to 0, then your y cap, if it is 0.01 close to the 0, then what will happen? This 0 into this particular terminology will be gone. Now this will be active. So that will become like again negative of log of 1 minus 0.01. So that will become negative log of 0.99. This will be a small number. Okay. And that is a small number because your prediction was close to 0. Imagine that what you have to predict is 0, but what you predicted is actually 0.99. What will happen? Then here what will happen? Negative log of 1 minus 0.99. That will become negative log of 0.01. This will become a large number. And that is because you have given a prediction which is close to 1, not close to 0. So that means the cross entropy loss will actually give a high penalty for the opposite like prediction. If your y is equal to 0, then your y cap should be near 0. Then if your y is equal to 1, then your y cap should also be near to 1. So that is what the model will actually do. And this kind of class entropy cannot be used for the SVM model because we want to externally enforce the model to actually reach the maximum margin. That cannot be done using a regular training. Okay. So for that, we have a solution in the SVM that is actually called Hinge Loss. Okay. In the SVM, if you want to train the model, we can actually use this Hinge Loss. Now, this Hinge Loss will be used for training the SVM model with again gradient descent. So the loss will look like this. Loss will be maximum of 0, 1 minus t into y. Now this t is actually the true value of the class. If the class is actually like t is equal to 1, it means it is a positive class. T is equal to -1 means it is actually a negative class. Okay. And the classifier score y. And this y is actually computed using W transpose x plus b. No activation, nothing at all. Okay. Okay. So now if you are using this particular function, then what will happen? Let's say that your t is actually 1 and your y is also 1. Okay. What will happen? Maximum of 0, 1 minus 1 and it will become 0. What you want to predict is 1. What you predicted is also 1. So that's why your model is giving a 0 error. So let's say that we want to predict t is equal to -1 and what you predicted is also -1. So let's assume that this is actually -1. Max of 0, -1 multiplied by -1, 1 minus, that will become maximum of 0, 0, that will be 0. So if you want to predict -1, then the model should be giving -1. Okay. But the thing is, since we don't have any activation, the model sometimes can give a high number, for example, maybe 5. Okay. So that can be something like a max of 0, 1 minus 5. That will become max of 0, -4. That will become 0. Okay. Imagine that t is equal to 1, but what you predicted is actually -1. Then what will happen? Max of 0, 1 minus -1. That will become 2. So now you are having a loss. You are having a loss for giving a false prediction. Similarly, if your prediction is actually should be -1, sorry, if your prediction should be -1, t is equal to -1, but the actual value you have given is 1. Then again, max of 0, 1 minus -1. That will become max of 0, 2, which will become 2. So you will receive a high error, and that is because you have given a wrong prediction. Okay. So the thing is, this entire model, if you train the model with this particular Hinge loss, it will try to enforce the model to actually give a value of 1 or value of -1. Okay. Any doubts? All right. So now again, this is just a loss function, but how do you maximize the model? How do you maximize? Sometimes it may happen that your model may like stuck somewhere. The model may actually like just behave like a logistic regression. Okay, we don't want to actually like let the model to stuck somewhere like logistic regression with a partial solution, something like this or this. We want to go to the maximum margin. Okay, so there is a easy way we can actually enforce the model. Every time you're actually doing something like 1 minus prediction into actual, right? So what we can do, if we give a high value here, for example, instead of 1, if we give 5, then 5 minus, here the 5 should be there. So t will be anyway 1 always, 1 or -1. Then your y value should be plus 5 or minus 5 depends upon the situation. Okay, so now if we are changing this particular activation, sorry, loss function max of 0 comma 5 minus t into y, if your t is equal to 1, then your y should be 5. Only then this particular function will become 0. 5 minus 5 will become 0. Again, if your t is equal to minus 1, then your y should be minus 5. Otherwise, what will happen? Either you will add something more than 5 or you will be giving something which is more than 0 to 5. Okay. So anyway, if you want to suppress this particular thing, instead of 1 you want to make it into a 0, or instead of 5 you want to make it into 0, then the y value should be increased, right? The y value should be more. If you want the y value should be more, then the w transpose x plus b will be more. That should be more. If you want this particular thing should be more, then the weights has to increase. And if the weights increase, it will actually never stuck up in this particular margin. If your weights has to increase, if it increases, then it will actually come to this place. Okay. So you achieve the maximum margin by actually giving this particular extra penalty, that your model has to give a large positive number or a large negative number. So again, in the SVM model, we are not actually doing any activation. It is doing a kind of regression kind of thing only, but it is just enforcing the value to be large positive or large negative. Okay. Any doubts? So how do you achieve like a maximum margin? You are trying to like put more penalty to the model, and you are just trying to build a model with a large value of w, and through that you are actually like enabling the model to explore more rather than stucking with some local minima which will give 100% of training accuracy. Okay, getting the initial 100% training accuracy is a kind of local minima. Local minima means it is not a global solution. Any doubts? Okay, so that will be like done by the delta 1 plus delta. Okay, so this delta is actually the margin. If you want to maximize the margin, you need to set this delta as a large number. If you set it as a large number, then your margin will be maximized. It will actually become in the middle of the both classes. Okay, but if you just don't give it, then your y will be restricted to value of 1 or minus 1. Okay, otherwise the weights won't grow. If you don't grow the weights, then the model will be stuck up with a partial solution. Okay, all right, this is the purpose of the maximum margin classification, and maximum margin classification is used in the other models also generally, but in the SVM they are specifically using it. Okay, and the secret sauce is the hinge loss, which you use it for training the model. Okay, so this particular margin value is actually represented as a C parameter in the SVM implementation. If you are implementing the SVM using any package, it is actually called as a C parameter. Okay, so if you put the lower C, then the model will be like allowing some kind of error. If you put a larger C, it will just like give a high penalty if you don't fit it well. So what will happen is like the model will actually fit exactly in the middle. Okay, so setting a large error for the model, C is like something related to the delta. If it is a large value, then the model will fit exactly, like 100% accuracy will be there. If you allow like some kind of error in the training by setting a smaller C, then the model will settle with like maybe 98% of thing. So you need to like think, sometimes a smaller C also means like this. We don't want an underfitting model which is like giving only 50% of accuracy during the training. So you need to like tune this particular C parameter, which is the hinge loss. Okay, if you set it too large, then the model will overfit. If you set it too small, then the model will underfit. Okay, So sometimes a larger C is actually very bad. You can see that because we set a larger C, the delta value, the model found the exact difference between the two classes, but we can just consider this is a kind of outlier. If we had some kind of relaxation, maybe this model is a good model. Okay. Maybe this is one sample which is an outlier from the class 1. So again, this is a trainable parameter. This is a hyperparameter that we have to find. We need to find the proper value. Okay. So I don't want to go through this particular thing, how the gradients are computed when you want to do the training. Okay, now we are coming to the second part. How to use this support vectors. How to use the support vector in the support vector machine. So let's say that you have a nonlinear data where the separation cannot be done linearly. So imagine that you have two classes where this is looking very funky, like this is one class, this is another class. Sorry, this are the same class and these two are the same class. Using a linear model, you cannot separate them. Okay. Now you have two options. Can you train a nonlinear model which can actually do like this, or make the data linear? What do you think? How do you deal with this kind of nonlinear data? If the data is nonlinear and your model is linear, how do you want to deal with this? Can you train a nonlinear model, or we want to make a data linear? Yes, madam, please go ahead.
Polynomial function we can use.
Yes. We can actually use a polynomial function. So the polynomial function will be used for making the data into a linear data. You know, sometimes data is nonlinear, but if you project the data in a higher dimension, it will become linear. So let us see like how we can do that. So those were the original dimensions. Now we are actually projecting the same data in 3 different dimensions. You simulate like x1 square as x1, x2 square as x2, and then root of 2x1 x2 as x3. And if you do this transformation, you are not now dealing with the x1 and x2, you are dealing with the 3 new dimensions. And if you project all the data samples in the 3 new dimensions, now we have a clear separation. It's the same data projected in different dimension. You know, I'll give you an example. Something like, for example, somebody is there, like, and you have properties like x1, x2, x3, x4. Okay. These are maybe the physical properties, something like height, weight, and then like a skin color and all. Okay. So now you don't like see a clear like a picture through this outward like a simple data features. So what do you do? In your mind, you imagine like a certain criteria, something like how physically strong is the person, how physically attractive is the person, how mentally attractive is the person, and then you try to project the data. So you try to like maybe think of 2 or 3 combinations of the input and then try to give a new dimension. So like maybe the physical attractiveness. So you try to combine like both height and weight and skin color. Then there is like a mental ability, something like stress level, and then like IQ. Maybe that is like a 2 feature. You try to combine it and then consider it into a 1 dimension. So there it will actually become much more like separable or like visible. So this is something called a subspace projection. Subspace projection means there is a larger dimensional data which you are projecting in a smaller dimension. So in our mind we have a subspace projection. Okay. Similarly, we can do a polynomial projection for the data to project the data in a higher dimension, and there you will have a separation. You have like 2 classes which are separated here. Now is it very easy to fit a model which is actually linear to separate them? Okay, that's a simple thing. We can just run a SVM on this high dimensional data with the simulated features x1, x2, and x3, and just have a model. And if you are fitting the model, then if you try to project them in the original space, the boundary will look like this. You know, this is actually the same model. So the decision boundary has now become like non-linear because you have done a linear classification in a higher dimension. Okay. So this is actually the polynomial like projection of the data. But there is an issue with the polynomial projection. So can anybody tell me like what is the issue with the polynomial projection? There is an issue that most of the time we don't actually go for the polynomial projection. Yeah, so this is actually the maximum margin classification, and your margin like this, and these are all the support vectors. Can anybody tell what is the maybe the drawback of this polynomial projection x1, x2, x3? It is giving a separate like clear distinction, but there is a problem. Accuracy may be kind of, there are like some like logical problems. I am just giving you that okay, so there is like x1, x2, you take the square of it, and then there is like a root of x1 and x2. So this third dimension is also one good possibility. This is where you have the like most of your discrimination, like all your like red data becomes higher than the 0, or your blue data becomes lower than the 0. This becomes like a very important feature. And if the data contains like maybe 100 features, x1, x2, x3 up to x100, it is not possible to find like what combination we need to do and what polynomial degree we have to go up to find like whether the data will become separable in that particular dimension. That is actually the simple problem from outside. Okay, and imagine that you just want to go with like x1, x2, x3 up to x100, and you want to add x1 square, x2 square up to x100 square. Then what will happen? Any problem with that? Like because we work in the S square, not in the original data. No, actually, like the original data will not have any accuracy, but the projected data will have accuracy because it is separable, right? So the problem is actually not with the accuracy part, the problem is actually the computation part. It is not very easy to find what kind of polynomial projection that we want to do. We want to do a root of it, we want to do cube, we want to do square or power 4 or root of 2 features and multiplication of 2 features. I don't know what kind of combination. There can be maybe for 100 feature, there can be like maybe 5 or 6 different kind of combinations, or maybe 500 different combinations. And you cannot keep on adding like a lot of new simulated features. You know, this is actually the original data. This is the square, x1 square, x2 square. If you have 100 feature here and addition 100 more feature, then you have like a theta 1, theta 2 up to theta 100. For x1 square, it will become like theta 101, theta 102. It will go up to theta 200, you know. So the model has become 2x larger than the previous one. And imagine that you want to go for x cube, then what will happen? Your model will actually have up to theta 300. It will become like 3x. The model will become too complex because of your lot of simulations. And don't really think about the combination. You have like x1, x2, x1, x3, x1, x4, x2, x3, x3, x4, x4, x5. You can have any number of combinations. You don't know what combination will work out. Okay, that's why people don't most of the time mess with the polynomial regression. They don't mess with the polynomial regression. Yeah. Okay, so this is where these people, these tiny little people who are on the border of your model, these people come into the picture. This is where the support vectors actually come to the picture. You know, this is the issue. So the support vectors are actually going to be working for you to do a trick. So in the data set, we need to add new dimensions. Okay, that is very clear. So we have x1, x2, x3. We want to add new dimensions. And those new dimensions should not be just x1, x2, x3 or square of it. we want to simulate a new dimension, which is like computationally feasible. Okay, so what we want to do, let's say that this is your original dimension x1, x2, x3, x4, x5. So for all these you will have like theta 1, theta 2, theta 3, theta 4 and theta 5. Okay, all these are your samples. These are your samples or your data set, you know. And with this sample what you do is like you try to like maybe build an initial model and find that these are all the 3 support vectors nearby the line which you built it. Okay, so those support vectors may be like this and this and maybe this. Okay, let's say that these are all the 3 support vectors. Now what I want to do, I want to create a new column x6 for this support vector. So what I will do, I will take this particular row value and do a dot product with each and every sample. So I will just take this particular row value and then do a dot product. Dot product means like a 10 into 12, 530 into this one into this one, this one into this one. You take a summation value and then you are going to fill it here. Now again the image 4 dot product with this one. Okay, I am going to fill it here. Again I am going to fill it here. Dot product with the same sample, I'm going to fill it here. Okay, so what you do, if there are like maybe 100 samples, you take a support vector 1 which you computed using your initial model and try to do a dot product between all the samples and then create a new column, and that will be your x6, that is your theta 6. Now what I will do, I will take the support vector 2 and repeat the same process. I will take this vector and then do a dot product with each and every sample. Now that will become x7 and that will become your theta 7, and again some real values will be given here, x8, and that will become your theta 8. Okay, so now what will happen, you have a main model which is based on your 5 features, and you have like some more discriminating features which are from the support vector. Okay, and these support vectors, since they are actually close to your margin, they become a better discriminative feature for the model to discriminate between 2 classes. These are the like few of the key people who are like in the border. If you find the similarity of this person by multiplying the dot product, what will happen for this guy SV1 support vector 1, his dot product will be more or less similar to all the samples which are belonging to this class. And since he is like a little bit away from this other class, his dot product with the other samples, they will become totally a different number. So again, if you are doing like a dot product for this support vector 2 which is here, for the same class, the support vector value like we are computing, this will become like maybe in certain range. Since it is like far away from the other class, the multiplication of support vector 2 with the other class, those will be in a separate range. Maybe these are in 1 to 100, and this will become like maybe minus 100 to 50, something like that. So these support vectors become a discriminative feature, and you separately train again few more parameters for each of them. Okay, now doing the dot product and then adding new dimensions through the support vector is actually called a kernel trick. You know, the kernel trick, what you do, you take 2 vectors and then take a dot product and then add it as a new dimension. That's it. Okay, so there are many ways you can do the kernel trick. There is a linear kernel which is actually the there is a reason why it works, because if you do a dot product of this particular vector with this one, this one, this one, this one, since this is close to this other people, then the value that you are adding to the like column, like maybe x5, all the values that will look similar for this class, and since it is very far away from the other class, then these set of samples will have a different value for this multiplication. Okay, so this is why the kernel tricks actually works. Okay, so if you are training the support vector model in the sklearn package, it is a package in the Python language. So after the training, you will actually get the number of support vectors and like list of support vectors, the number of support vectors, dual coefficient and the coefficient. Now the coefficient is nothing but your theta parameters, which are actually from your data set itself. These are your coefficients. Okay. Dual coefficients are the coefficients which you compute for the new dimension, which are these. Theta 6 to theta 8 are the dual coefficient. Theta 1 to theta 5 are the coefficients. Okay. So now why we are using the support vector? Support vector becomes a discriminative feature. Instead of going for a polynomial transformation, we actually project the data in a higher dimension using the support vector. You know, if you have 100 like features in the data set, if you are using polynomial degree of like 2, your samples will become like 200 dimensional. You are increasing it 2x. Imagine that the data set contains like only 5 support vectors. Then you are going to just add 5 new columns and your model will become like 100 to 105, because you added new 5 dimensions for each support vector. Okay, and the number of support vectors will also be smaller in number, so your model will never become like 2x large, but still the model will be projected in a higher dimension with better discriminative features. And these support vector goddamn its are the better discriminative features because they lie in the border of your model. Getting it? So this is why we actually use the support vector to discriminate your classes. Any doubts? Okay. So if you are training the model in sklearn, after the training you can just check it out. So usually you will do something like a CLF dot like fit, that is a model, and then you can just put like CLF dot coef underscore, that will be the regular coefficient, which is the theta values or the W values, and there is a dual coefficient. Dual coefficient of the support vector in the decision function multiplied by the targets. Okay. All right. So these are other kernel functions. We can do just a dot product in the linear kernel. So we have other kernel functions like a polynomial kernel where we can do a dot product and then projection in a higher dimension. So that is like dot product square, dot product cube, something like that. But this is seldom used. But the most famous one is actually this radial basis function, which is exponent of minus gamma of norm of your 2 vectors and then take a square of it. Okay. And sometimes there is a Gaussian kernel where you find like exponential of minus of the distance between the 2 vectors divided by the like the 2 times the variance square. Sorry, variance. So this is a linear kernel, like the like influence of the support vector with respect to all the samples will be computed linearly. These are all the non-linear kernels, where if you are having like one sample and other sample and other sample, something like that. If you are using like Gaussian kernel, if this is the support vector, then all the samples which are closer by, they will get a higher probability or higher similarity because it will have some kind of like a Gaussian kind of things. This is your support vector and these are your other samples. So the output value, this kernel value, if it is the same sample, you will get a high value. If it is a like sample which is nearby your sample, then you will get like probably low value. If it is very far away, you will get a 0 value. So you can just imagine that what is the reachability of that particular support vector. Okay, so that is like I will reach up to here. So that will be the Gaussian kernel. So outside the Gaussian kernel, these people will receive like a 0 value for this support vector. So again, that becomes a discriminative feature if you want to train it. Okay, so there are a lot of functions, kernel functions. If you are using a linear CVM, then your dot product will be the linear kernel, and if you are using the non-linear SCM, then we'll be using the radial basis function, Gaussian radial basis function, which is very, very famous one. And this gamma has a really important thing. The gamma parameter will tell like what should be the squeezeness or the skewness of this particular distribution. Okay, if you want to consider the samples which are very, very close by only, then you can set a gamma value which is larger. If you want to maybe reach to a lot of samples which are very far away, then you can set a gamma value which is 0.01, something like that. So gamma parameter is a kind of hyperparameter which you can tune it. Okay, so if the gamma is like a small number, you will be reaching to larger places. If your gamma is a large number, then you are narrowing it down. If your gamma becomes too large, then everything becomes narrow. This is the influence of the gamma with respect to samples. Okay, and if you train the model with the linear SVM and you find that the model is not actually doing a good classification, you can directly change the kernel value as a RBF, and that will become a non-linear SVM, which will actually do a much better classification. Okay. All right. Any other doubts? Please let me know. So the support vector classification is what we have seen, and there is also one more thing called the support vector regression. I'll just clear it out in a very simple few minutes. Support vector regression is actually seldom used. People are not using it because it is actually a stupid concept. Okay. Support vector classification works because they use a maximum margin classification, and they do this support vector projection also. That will help you to do the better classification. But support vector regression is actually a slightly a different idea. The support vectors are going to be used for a different purpose. Let's see what they are actually doing. Whenever you are actually training a model, you are actually computing the error for all the samples, right? Whenever you are training the model. Okay. So now in the support vector regression, what we want to do, all the regression, this is the problem of regression, we are fitting the line for the data samples. So what we want to do now, we will draw a line. Okay, and whatever that is within this boundary or the margin will become your support vectors. Okay, and if you are fitting the model, you are not going to consider the support vectors to find the cross entropy loss or mean squared error. Okay, you are not going to consider these samples when you compute the error. You are going to consider only the other samples. Okay, so the only way you can fit these samples also is by including them into this particular margin. So what the margin will do, we will try to adjust the model so that you will find, or you will try to put maximum number of samples within the margin, and through that you are trying to fit maximum number of points using the model. Okay, so now this model will have only lesser number of support vectors because they are very lesser in number. So what will happen is this model will receive a larger error because other samples will actually give a error. And now if you adjust the model may become like this, and if all the samples are actually within this margin, then you will not receive any error. So this is on the air you have some kind of thing and you want to cover it, so you are trying to build a pipe which will include everything. This is a virtual pipe, and you are not going to get any penalty for the samples within the pipe. The samples within the pipe are going to be called as support vectors. Okay, so that is the thing in the SVR, that your penalty will be more for samples outside, and you try to fit more models or more samples within the margin. And this is why the SVR concept is actually a failure model. Nobody uses the SVR. SVM for classification is the better one. Okay, for regression people don't prefer the SVR. All right, so that is my presentation, and if you have any doubt, please let me know. Okay. So if you are sleeping, then please wake up. Session is over. Yes, madam.
Thank you, sir. Thank you very much, sir. Student, do you have any doubt? If you have any doubt, you can discuss. I think, sir, no doubt. Yes, ma'am.
Yeah, I just want to thank Sridhar sir for all his analogies, especially marriage proposal. I'm sure all the students would have enjoyed it. Thank you very much, sir. Thank you.
Yes, madam.
Yeah.
Thank you, sir. Thank you very much, sir.
So thanks to all the participants, students, friends, faculties. Thank you, Mr. Akshay.
So keep in touch with us always.
Sure, madam. Sure.
It is Pimpri Chinchwad College of Engineering, sir.
Yeah, madam. Yeah. Yes.
Fine. Thank you, sir. Thank you.
I am very much like in conversation with Dr. Swati Sinde also. So
Oh yeah.
she's a very good friend of mine.
Fine. That's good. That's
Yeah, madam.
fine.
So
sir.
thanks.
Yes.
Thanks to all the buddies who are commenting. Thank you, Deepali, Ajinkya. Thank you all. I had a really great time.
Yeah, sir, if you can share your mail ID, sometimes students may get in connect with you. Maybe they are.
Sure, madam. Sure.
If you can share on chat.
Sure, madam. So maybe within a month I'll be releasing a Udemy course, and that will contain this marriage proposal and everything as a nice
Is
story.
it so?
Yeah, madam. Yeah. So the recording is going on. It will be released very soon.
Right. Fine,
Yeah.
sir.
Yes.
Thank you. Bye.
Thank you, madam. Thank you so much, and thanks all buddies.
Yeah,
Bye-bye.
thank you, Sushma madam, and thank you, dear students. Hope that was useful. Prepare a presentation. We'll see later. Okay. Bye.
Thank you, ma'am. Thank you,
Thank
sir. Thank you very much.